Everybody good with that? Those are random algorithms. All right, so now we're going to talk about time complexity. And right back on Euclid, when he came up with his algorithm, he didn't care about, well, you know, I say he doesn't care about it, but the truth is, if you take 3101 from me, I'm going to give you a Euclid algorithm, and then I'm going to argue that that Euclid algorithm, though reasonable, takes exponential time. And then I'm going to give you a new algorithm that takes n squared time, where n is the number of bits to write down the number. All right? And so which algorithm did Euclid tell the world? He told the world the fast one. He was doing it by hand, right? So yeah, he cared about running time. He maybe cared about running time more than we did, but he never talked about running time. All right? All right, then Turing came along and proved that the halting problem, again, up until here, there's still what is computable and what's not computable. There was no thought about running time, right? Only to the extent of what were humans willing to actually compute on paper, right? And then this here is me. This is my father. And he, about the time I was being born, he came up with the idea of running time, all right? He said, what you can do in polynomial time, we're going to define to be computable. A reasonable, not computable, this is computable. He's going to define to be a reasonable algorithm, right? Feasible. And what takes exponential time is not feasible, all right? So these are the slides I made for 1090. Not 1090, you're 1090. 2101. Actually, that also is a lie because I made them for 2011, but the course changed name. All right, so here, time complexity. There's what problems you can solve in constant time, and that means where it doesn't matter, there's some number 5, a billion, trillion, and you never take more than 1 trillion time, no matter how big the input is, right? And then log n is binary search. Linear is the time it takes you just to look at the input. If your problem requires to know what the entire input is, then it takes at least linear time, right? N log n is the quick sorts, the slow sorts, and then this is polytime. It's into n squared is polytime, n cubed is polytime. Actually, into the trillion is polytime. And you might ask, why did my father say that into the trillion is a reasonable time algorithm? Because clearly it's not, right? And the reason is because in practice, if you find a polytime algorithm, then it might be n cubed, it might be in, but I can't tell you right now off the top of my head a polytime algorithm that takes n to the 4th time, right? And in fact, even the n cubed ones of matrix multiplication is a lie because your input then is of size n squared. So really the running time is n to the 3/2. All right, feasible. Exponential is definitely not feasible. We call it brute force, where you're out there, bang, 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 you're searching for all possible solutions, right? And then you can get what's computable, right? And then you get the halting problem. Everybody good with that? Right, so constant time, log time, linear time, n squared time, exponential time, right? Here's just a little graph, and you can see that even n squared time gets kind of scary when your input gets big, right? So, for example, when they're doing machine learning and the input is the size of the internet, It's possible that they're doing n log n, but they're certainly not doing n squared, right? And then you see with exponential growth, it just gets to be absurd, right? Everybody good with that? All right, you've seen these. Here's various sentences that we want to be able to write. We want to write problem P is computable. It's computable in constant time. It's computable in poly time, exponential time, right? We want to talk about the class of exponential time. We want to say the exponential class has more computational problems than the class polynomial, right? That's why we drew the circles bigger and bigger, right? Because if I give you exponential time, there are more computational problems that you can compute, right? Everybody follow this? All right. You've seen this notation. Everybody get this already? Here, this is my algorithm on input I. What does my algorithm on input I output? This is what the stated computational problem, sorting. What does it want? What output does it want? And this is saying they're the same, right? This is saying my algorithm on input I gets the right answer, right? This is saying how many time steps does my algorithm on input I run, right? What does this say? This is some function which is going to be my time complexity, like n squared, right? Everybody good with that? Are we going too fast? Are you guys good? Excellent. All right, problem P is computable. We've seen this already, right? There exists one algorithm that on every input gives the right time, right? And here, I mean, this is a very powerful game here, right? You say there exists an algorithm. What's the requirement on the algorithm? The only requirement is that it has a finite description, right? The description could be a billion size Java code, right? Is that legal here? Yes, it's legal. But you give me a big algorithm, I'm going to give you an even bigger input, right? Remember that table lookup problem. I could give you a really big table, and I will find an input that's not on your table, right? Everybody see that? All right. So now we want to say it's computable in n squared time, right? So what are we saying? There exists an algorithm such that you give me any input, it will get the right answer, and the running time is at most n squared, right? Everybody buy that? And then we have to say what is n. That's switched, right? In addition to getting the right answer, the time is bounded, right? Which n? What's n here? Right? N's the number of bits to write down the input, right? So I'm going to replace that out because we don't need an extra variable, right? This says no matter what input you give me, the running time on that input is at most the number of bits to write the input down squared, right? Is everybody following this one? Because it's only going to get harder, right? Right now, it's not computable in n squared time, right? Now, again, people are going to write down so many things, right? They're going to write for every algorithm, if m solves p, then it takes more than n squared time, right? You could write something like that. You could say, for every algorithm and every input, if it gets the right answer, then the time is big. Is that going to work? Right? You give me an algorithm and an input. If it gets the right answer, then on that input, the time is big. Right? Think about table lookup. Right? I can give you an algorithm which is just table lookup. And on some of the inputs, it's going to get the right answer fast, which kind of breaks this, right? How about this one? For every algorithm and for every input, so for every algorithm, if it gets the right answer on all inputs, i.e. if it solves the problem, then on all inputs it takes a long time. Right? Is that good? Yeah, you're getting ahead of us. All right? Right? Do these guys work? Right? Do they express what we want them to express? I'm claiming they don't, right? I'm claiming all of these, in fact, are true for the halting problem, right? Oh, are they true for the... yeah. Sorry, they're all false for the halting problem, all right? Why? Because at least they don't express what we want. I can design an algorithm, right, such to make, what do we have to do? We have to get the left side true, and we have to make the right side false. I lied. I can't do this for the halting problem. I can do this one up here for the halting problem. I can't do this one for the halting problem. But take some problem that takes exponential time, right? All right. What? Right? This has to be true, right? So here's my, right? Let's take some fancy input. Take your input, which you think is weird and has lots of bits, right? And somehow offline find out what the answer is, right? And then what is machine? Well, if the input is your fancy, it's table lookup, right? If the input that you give me, I'm designing an algorithm. You give me an input, right? If my input is this fancy input, then I know the answer and I output it quickly, right? If it's a different input, then I take all the time in the world to solve it, right? Everybody get this algorithm, right? Is this true? Yeah, on every input, it gets the right answer, right? Everybody agree with that? Right? Because here, it might take a long time, but it always gets the right input answer, right? And is this true over here? No, it's not true on every input. It takes a long time. There's this one special input where it's fast, right? Everybody buy this? How many people are following what we're doing here? You guys following this? Right? What am I trying to teach you? Logic, right? We're trying to teach, what does a sentence like this say? And it doesn't say what we want to say, right? And so my bet is if you try to write down how do you say it doesn't compute in n squared time, you're going to struggle. And so how do you do it? You do what I think he did, is you just take the negation of it, right? And that's where taking this course helps. All right, so what's the negation? You turn the exist into false and the false into exist, and the ands, remember you turn the ands into ors, and you turn the equals into not equals, and the less than or equals into greater thans. Right, everybody take the negation of this, right? And then we play the game, right? We're going to say P is uncomputable in n squared time. Why? Well, because every machine fails to compute it in n squared time, right? You give me a machine, that machine doesn't compute my problem in n squared time, right? Why does n fail? You give me a machine, why does that fail? It doesn't have to fail on every input. It has to fail on one input. There just has to be one input in which it gives the wrong answer, and it's bad, right? Right? And why does it fail on that input? Well, either because it gets the wrong answer or because it takes too long, right? Does that make sense? All right, you give me any machine, I look at the machine and I find an input in where it doesn't work, right? either because it gives the wrong answer or takes too long. All right, everybody following this? All right. All right. So now we want to say it's computable in constant time, right? So what constant time mean, right? Here's, Gödel knew what constant time means. In fact, to tell you a little politics here, my father says that he invented this problem. Well, really, Gödel invented it 20 years earlier. All right. All right. So, right, the idea is that constant time doesn't depend on the size of the input. And is this constant time? Those who haven't seen it before, it doesn't look very constant, does it? Right? Why is it constant time? Because you took the course, a different version of the course from me, right? It's constant time because it's bounded by a constant, right? If on some inputs you're a little faster, that's great, right? So here, the time is bounded by some constant, all right? Now, everybody got that? Now, which constant? So we have to say, who gets to decide the constant? Or you have to say, are we saying for all constants? Or are we saying there exists a constant? How many people want to go exists a constant? Anybody want to go for all? No, you don't. All right, so if it's an exists a constant, do we come up with a constant here? Or do we come up with a constant here? The key is, so I have the next set of slides are coming up soon. It's going to be the idea of runtime versus compile time. All right? And what's the difference between runtime and compile time? Anybody want to guess? Here's time going this way. Exactly. Compile time happens before we know what the input is. Runtime happens after the input. And you'll see I have two nice blanks here. This here, compile time, happens after we know the algorithm, right? You give the algorithm, the Java program to the compiler, and the compiler has to find the compile time errors, right? Versus then it compiled, and then you run it. And then when you run it, you have an input, and you find runtime errors, right? So we're going to say exists. And if we say exists, then that means that the algorithm guy gets the algorithm gets to decide the constant, right? The algorithm can the algorithm say the constant is 1 billion? You get 1 billion times. Can it say that? Or does it have to say 5? It can say whatever. It can say billion. But when does it have to say it? What? Yeah, it has to say it without knowing. It's the same game we played before, right? Right, so here, let's back up our slides. We write big O of 1. It doesn't grow with the input. It's okay if it depends on the input, right? Who chooses the constant? Do we say the adversary gets to choose the constant? But no. If the adversary was going to choose the constant, which constant would he choose? 0, right? That would be bad. Right? Everybody see that? The adversary is trying to make it wrong. He's going to give us a small constant. Now, we could require that the constant's bigger than 0, but then he would choose it to be 1 or a half. All right, so now clearly the algorithm designer gets to do it, right? Doesn't have to be every constant, it has to be some constant. Now, right, example, not 1, right? Could it be 1 million? Yes. He says million's not fair, but million is fair, right? Why? Because it can't depend on the input, right? The constant, who chooses it? Does he choose it here? Is this right? Everybody say, no, this is not right. right? That would be unfair. You tell me the constant. In fact, this is true. You give me any input, there's some running time, and there's some constant, some integer that's bigger than that, right? All right, no, right? We need the constant not to depend on the input, right? Everybody get this here? All right, so here we're talking about coding phase, right? I said composing versus compiling, right? Composing, when the guy here is coding up his algorithm, he gets to define the C. He's going to say, I'm designing insertion sort, and I'm making C be 2, right? Before I know the input, I'm going to say the running times. All right, so let's play the game. So the boss, here P, what is P in this thing? It's a free variable, right? So the sentence is saying something about P. It's saying P is computable in constant time. And then how does the game play? The prover needs to have to come up with the algorithm and come up with the C. It says here, push and pop are on a stack. I can do them with at most 12 operations, right? Can make the C as big as he wants. And then he says, that doesn't seem fair. And he says, yeah, but it's got to work for all inputs, right? So he comes up with an input that's even bigger, right? And he still has to solve it in this much time, where his input's the size of the universe, right? Everybody good? Right? You see where in fact, people and friends of mine in the world know that I do math. And they want to come up and say, great, what is 378 times, right? No, man, I don't ever look at numbers. I look at 0, 1, pi, e, n, right? -1. I don't look at numbers. We only look at these logic statements, right? No numbers involved. And what was the advantage of this? Is that when we went from Gödel, who had no computers, to now we have crazy fast computers, the logic still works, right? It has nothing to do with particular numbers. All right. All right, so what was the definition of feasible? Polytime, right? So we want to say it's feasible if it's computable in polytime. So what should I put here instead? Right? Everybody good here? It's polytime. These are all polytime, right? And that's into the C. Right? Now, if we really want to get pedantic, we can talk about inputs being small and about the constant in front, but we're going to slough all that under the rug. All right? Which C, during the coding phase, I'm coding now. I talked about quicksort, insertion sort, and I said 2. That was for this one, right? Here, I'm coming up with insertion sort. I know it takes n squared time on every input, so I come up with C equals 2, right? And that's the game, right? Which n? Well, n's the number. Oh, we're doing this again. All right, everybody good? Everybody see that? Understand the game again? Right? During compile time, I say I have an algorithm. This why is sorting solvable in polytime? Because I can come up with an algorithm, insertion sort. I can come up with a C2, since no matter what input you give me, it sorts correctly, and the running time is bounded by the number of bits, or the number of numbers raised to the 2. Right? Everybody good? Anybody not following? You guys are just not a friendly bunch. All right, exponential time, right? We're going to do the same. And see, these are all exponential time, right? And we're going to just do that, right? And you might argue, why do I put a 2 there? Well, because I can bring the 2 up and down. There's ways of moving, right? You can transfer the 3 up. Yeah? All right, good. Some of you, right? So one thing you need to know about a proper big O notation is that they worry about, well, it doesn't, here we're saying, here F is theta of G. Why? Because it's bounded between some constant times G and some other constant times G when N becomes reasonably big, right? For small inputs, it might be wrong, but we're not really gonna, right? Why is it wrong for small inputs? Because, well, you got to set up the problem. You got to do some initial stuff, right? It takes a little bit of extra time, right? So there are various ways of fixing that, and we're just not going to worry about it. All right, everybody good? All right, so now how do we say it's not computable in polytime, right? Again, it would be hard to do on your own, but you just take the polytime and you negate it, right? So here is what you can do in polytime. Here you can do what you can do in exponential time. We want to say there is some problem. There it is, problem P. There is a problem P that can be done in exponential time and can't be done in polytime, right? Right? P, how do we say? Which P, right? We're going to see there exists the problem P, right? Here we're just writing it down. Everybody follow this? There exists the problem P that can't be done in polytime and can be done in exponential time. People see this? And for those of you not shaking your head, let me warn you that we have an exam coming up. And I believe that if you're in computer science, you need to be able to write this down, right? Why do you need to be able to write it down? Do you need to be able to memorize it? No. Should you understand first order logic and be able to read it? That's what this course is about. Should you know what it means to be in polytime? Absolutely, you need to know what it means to be in polytime. Do you need to know that there exists a problem, right? This is actually a true statement, right? Here's actually the funny, let me tell you the funny reality. Remember so I gave you homework over the weekend, which Simon looked at, which is proving a statement using merge sort. And what is that? That's called a constructive proof, right? How do you prove something exists? You construct it. So I'm thinking about adding to that homework because I haven't done it. I just thought about it after, stating the fact that mostly what we do in this course are constructive proofs. That if I ever tell you something exists, then more or less I do it by giving you an algorithm to construct it. All right? So this exists to P as a non-constructive proof. It's a counting proof, right? If I count that I have 10 pigeonholes and I count that I have 11 pigeons, I know there's a pigeon that doesn't have its own hole, right? I got more pigeons than hole. Some pigeon doesn't fit, right? So the way we're going to prove, we would prove this, is a counting argument. You count how many polytime algorithms there are, and you count how many problems, actually you count how many polytime algorithms are, how many exponential time algorithms, and they're just more exponential time algorithms, right? And so there's got to be, by counting, right? We know there's something in exponential time, but not polytime. But the amusing is, we can't tell you one. We can't name one computational problem that we know takes exponential time. We have plenty that we think takes exponential time, but we can't prove it. Right? Everybody good with this? Don't walk into the podium unless you want to amuse people. Here, let me tell you, yeah. Kind of lied in there a little bit. Don't try to work it out on your own. All right? It's actually, there's this idea of a diagonalization proof that Turing came up with. If you know the proof that the halting problem is uncomputable, you tweak it slightly and you get this proof. But it involves with, we're listing things here and we're listing things here and these, right? It boils down to a counting argument, right? But I did kind of slap a lot under the rug. Why? Because we're not doing it, right? But I think it's good to know that we have a concrete problem, the halting problem that is uncomputable, but we don't have a concrete problem that can't be solved in exponential time, right? But we know they exist, right? In fact, if you take a random computational problem, what does that mean? For every input, you flip a coin to see if the output's yes or no. It's undecidable, right? I mean, that's for sure. It's just like a random real is not an integer. It's not a fraction. All right. Everybody good with this?